evening, wherever you may be joining us from today. Welcome to day 3 and the 4th session of PV Magazine Week Europe 2025. And not to worry if you missed any of day 1 or day 2, these will be available on PV Magazine's YouTube channel very soon. And we have held some really great discussions, interviews, panels, and presentations already this week covering renewables and grid integration, new technologies in PV project operations, and ensuring project level quality and bankability. And lots more to come in live sessions this afternoon and tomorrow as well. So check those out later. For the next hour and a half, though, we are focusing on solar cell technology, always a fascinating and rapidly moving field, and one that is really at the center of the world's energy transition. Coming up in this session, we will hear from Huasan's Christian Gomez about heterojunction modules and how using these in vertical PV installations plays to the technology's inherent strengths and can result in system-wide advantages. We'll follow that up with a short presentation from Crew Group Senior Research Analyst Molly Morgan, looking at how the market today is split between different technologies and how we can expect that to develop over the coming years. And that's leading into a panel discussion where Molly and I will be joined by Radovan Kopacek of ISC Constance and Ed Crossland from UK-German tandem cell specialist Oxford PV. And we did have Fan Bin from China's GCL Perovskites on the list for the panel as well. Unfortunately, he has not been able to join us today. But then we will round out this session with a look a little further into solar technology's future. I'll be chatting with Alison Ciesla from the University of New South Wales School of Photovoltaic and Renewable Energy Engineering about what's hot in solar R&D right now, and what we might even see making its way into mainstream production lines in the coming years. That's all coming up very soon. And remember, we are live, so please do share your questions for today's speakers using the questions function on Big Marker, our event platform. I'll be feeding questions into the discussions after our presentations and during the panel today. So please don't be shy. And right now, I will hand over to our first speaker for today and for this session. That is Christian Gomez of Huasan for a look at HJT and vertical PV. Christian, welcome, and over to you.
Hi, thank you, and thank you for the opportunity of talking today. I will present today something that is not specifically about the cell technology when you look at it straightforward, but it actually entails a concept that necessitates a very specific technology behind the glass. So let's go for it. We will present very little about our company because I think almost everybody knows Huasan. Then what is the mystery motivation that I want to talk about, how it can be solved, and then we'll get to a summary. Those few who don't know us, we are the leading manufacturer in heterojunction. We have 20 gigawatt of production capacity located in China for the moment. And we have a history that began in 2020, and we expect that it will extend after 2027, not just in heterojunction, but with tandem with perovskite as well. You may have seen in the news that we have released for this perovskite tandem our first results with very small cells over 34% efficiency and larger cells, production cells, at 29% efficiency. As everybody knows, and Ed will say later, it's quite difficult to keep the efficiency from one size to the other. You may have seen in the news recently as well that we introduced the much higher efficiency and higher voltage products. We will not talk about any of that today. We will focus on vertical photovoltaics. So why I'm talking about a different topology of installation? The motivation is the price of electricity. These curves that you see on the screen are the evolution of the average price of electricity in the market in each one of these countries, hour by hour of the day. This means that in average in Germany, in this case, if you look at the top left, you see that in 2025, the prices of electricity have been going down, but most greatly they are going down in the central hours of the day. And that is not a German thing. That is something that you can see it's happening in all of these markets. These are the largest photovoltaic markets, Germany, Spain, and so on. But if we go to the east part of Europe, representative markets are seeing the same effect, even if they don't have as much electricity from the sun as the Western countries. And this event, I want you to see at the orange bar. This bar here denotes what is the levelized cost of electricity for solar systems, and that LCOE is the number that we have been using for many years. That is a number that doesn't care about when the power has been generated. It's an average of all produced module power. When you see the lines going at the lower end of the LCOE, this means that a system that has been built for that LCOE selling below that price is actually losing money. And this is the situation that we encounter in Europe right now, that the prices of electricity in the central hours of the day are going down, and eventually they are going below the generation cost of photovoltaics. And this makes many people very nervous because not everybody has a feed-in tariff. Not everybody has a strong PPA, power purchase agreement, that sets a price of electricity fixed. And many of the people who build power plants are expecting that they will be able to sell electricity in the free market for a profit. And when they see that the trend goes to making this not possible, many financing entities say, let's slow down, let's not build these plants. And that is happening right now in many of our markets. There is a slowdown of any power plant from PV that is not built with a feed-in tariff or an auction or a similar structure of getting the money back. If we go into the future, normally we cannot do that. We have to assume those growing bars that we all know that they're never right. But in the case of photovoltaic pricing, we can do that. How? We can go to the Californian example. And in California, they have a little bit more, they are advanced compared to us. And if you see the prices of electricity that we have in Europe and compared to California, we see we are in California 2020. So look what happened there. Photovoltaic keeps on being installed, and now the prices have gone down even more. And when you put that projection into the price of electricity that we are having in Europe right now, you can see where we are going to. We're going into a situation in which for normal power plants that go to the free market, profitability is a question mark. I don't want to scare anybody. People who make the numbers, they already know this and they're worried already. So don't be worried additionally. But what is the point? The point is when you have a normal classic, I'm going to call it classic PV system, the generation of electricity here in blue on the right side is more or less at the time of lowest prices. This is not a good look. If you go to now for the first time what we are introducing, which is vertical installation, you see that we push the peak of generation to the sides, to the evening and to the morning, where the prices of electricity, they are higher. And that is the key message. This is probably the most important slide in the presentation. We propose that installations on free fields are made with vertical systems so that the electricity generated is more in the times where it's more expensive on the market. It sounds pretty simple, and it is pretty simple. But we will give you context so that you understand this deeply, and let's go for that. The first point is that these curves that we have here only work well if we have a module with very high bifaciality. And that is where the technology of heterojunction comes to be useful, because heterojunction can have basically as high a bifaciality as you want, depending on the design of the panel. We have, since a couple of years, modules that are very highly bifacial. Now we are, with the recent release of Kunlun, at 97% module bifaciality. This is both for modules installed in landscape orientation or in portrait orientation. So we have many modules that can fit any necessity in terms of mounting system. How is this special for Kunlun is in this slide. The first thing that we did is we did a cell that was more bifacial by having fewer fingers on the rear side. This decreases the nominal output power. So instead of having 730 watt, we have 720 watt nominal power, but it increases the bifaciality. The second point we do is we have either frameless or we have a different frame. You see it here on the bottom of the center. It is a frame that avoids shading the cells. And this is key because when we see what is the bifaciality as a number, it may be 80% and you think it's a good number, but it is not the same in real operation because the shade of the frame in real operation will affect the cells and the bifaciality number will be a fake number. This is much more pronounced for vertical installation than for normal installation because in vertical, the sun is actually on the rear side, casting a shade on the frames. If you take normal bifacial modules in normal installation, the rear side is getting diffuse light that does not get affected by these frames or junction boxes so much. We have found a difference of 10% more yield when we used a frameless module compared to a frame module, a classic frame like this, in the installation on vertical. This is a huge difference of real performance. The final point refers both to performance and to the most important, which is reliability. We put on the rear side LCF, light conversion film, so that you have not only a bit higher efficiency, but the cells are protected against UV. The last point helps nothing for efficiency, but it helps for yield. Again, it is to use anti-reflection glass on the rear side as well. And these innovations, in addition to the fact that we only use junction boxes that are rated to be withstanding UV light for all the years, all of this makes a vertical module different to a module that is not made for vertical, but you can install vertically. So as you read this, you can imagine that it is much more useful to get a module that is made for vertical installation. So after that, let's go to the analysis to see the context of this great idea of doing vertical. What is the context? The context is that we can do many types of installations. We can do fixed tilt. We can do trackers. We can do east-west fixed tilt. We can do vertical. And all of that can go with or without a battery. And all these 8 scenarios is what we have simulated to see what is most convenient for the customers. And when we did that, about the yield, we've seen that tracker, obviously, if you don't have downtime, have a much higher yield than fixed tilt. This is no surprise to anybody. The question is if you want to go to trackers because of the moving parts and all of these other considerations. And we found that when you do east-west fixed tilt, it is not a very good result. I had to repeat the simulation 3 or 4 times to make sure that I was not tripping, that this is really what's happening. And it is a fact that the dome east-west really loses quite a lot of yield, partly because the bifacial effect is very reduced, but mostly because, well, it's doing like vertical, but with 2 panels instead of 1. And if you go vertical, you have roughly the same yield as fixed tilt south. This is only this way because we are talking about 97% bifacial modules with a very good bifacial performance, not a normal module. So this is the scenario where we start. You have this kind of yield, but that's just yield. How much money is that yield going to make you when you go merchant to the market? And you can calculate yourself. These values are available on the internet, and you can run your own simulations. And we did that for Germany, and you can see here the results. The fact is, for 2024 and 2025, installing a battery, and in this case, we took a battery with a very low cost of turnkey 14 cents per watt, really very, very low price. You can only get that if you are doing utility scale at a very low, very good negotiation. If you do that, if you take this, it is still a worse return on investment as compared to doing without a battery. As of today, we have seen from California that the trend continues. So probably this will be in the future a good investment, but for now, it is slightly worse. But the more important point, that is the second thing of today, is that when you compare the profitability today, and you see this in the 4th bar, of doing vertical, it is higher than doing fixed tilt. It is a little bit lower than doing trackers, but this is taking into account perfect reliability of the trackers. And people who have trackers will know what I'm talking about. This is a Excel value for the trackers. You need to see what is the real result afterwards. And of course, you can still put a battery on a vertical system, and that is still more profitable than today having a fixed steel facing south without anything else. When you look at all the possibilities, you can see that there are two winners. The first one is trackers, the second one is vertical. And then comparing both, you can see that the vertical will bring you the advantage that it really produces at a very early and very late time of the day. So you are more protected than when you use trackers against the low electricity price in the future, and that you don't have moving parts, which is, let's say, just a risk to your calculation and probably a thing you need to think about when you're looking at the longevity of the PV plant, because typically a tracker only gets a warranty of 10 years, maybe you get 15 years somewhere, but it is a moving parts element that is not going to be expected to have the lifetime of a fixed system. So that is the summary of what is the profitability today. And you can see that this is done with today's prices, where the mounting system for vertical is still very, very expensive. But it is coming down. It is coming down because larger projects are being planned and executed, and this will bring down even more the price of the structure when you have fixed structures and trackers that are basically as optimized as they can be, and they will not be lower in price. So even going deeper, because we have the 2 minutes left to do that, I took the time to look not just at simulations but real data. And when you took for 2023 the actual irradiance in a place, and you take the actual yield of a PV plant in that place, not just simulations for any year that are always a little bit misleading, right? Because, well, the price of electricity actually seems to depend on the weather. Then you see that this dependence on the weather, it is a reality. This is 2023. Because 2024, well, the data is not ready yet. I hope it will be soon. But you can see that when your PV system was performing very badly, this means in the very early morning, the price of electricity was on average quite high. And when it was performing perfectly, it was very low. This includes summer versus winter. This is for the whole year. And this means that there is a correlation, very clear mathematical correlation, that says that when you produce most in fixed steel, you get the worst price. And this is not great, right? This is really not great. If you go on the right side to what is the dependency, when you calculate exactly the same with vertical, you see that there is a dependency, yes, but it is then broken. For the moments where you produce the most, morning, evening, this is not such a dependency anymore. It is almost flat. So you get, because of this relationship, that is why we say that you get a better price protection. Because that moment in time where you're producing the best, it is where you are not so getting such a variation of your electricity prices. And that is the key why we think that if you're planning any kind of PV plant on ground, even not considering agrivoltaics and the dual use of the land, even forget about that. You should consider vertical to get a better return on investment already today, but especially on the future. And please keep some land for maybe having a battery farther down in the future. But if your company, as an example, today is maybe not so sure about being able to do a huge utility scale battery well, or if you're not sure about the return on investment or the legal framework that will rule over your battery, you can already go with vertical and have some peace of mind that you are doing already today what is best to protect your investment against very low price of electricity on the market. These are the graphics that show how different the generation, this is the light blue on the back, of vertical is compared to all the other topologies. And this here is the money income compared to the generation is a little bit different. And you see how the money is done. this graphic here shows the differential of income hour by hour from vertical to south. And you see in the morning we get much more money. We basically lose that extra income during the central hours of the day because the price is still around the LCOE value. It's not like we don't get any money. But then in the evening, we get the true advantage of vertical. And the end result is, of course, that we have much more income. It is about 20% more income. It's just that because the PV plant is more expensive, the added profitability is not 20% better, it's a little bit less. So what is the final words? You can get better price protection with vertical than batteries as of today. You can have a vertical PV plant with lower cost than adding a battery or using trackers. And all of those possibilities will give you a better profitability of vertical already today. So this is our contribution to the discussion of how to improve moving forward power plants. And we think that vertical should be really the default consideration for on-ground systems, not just because of this, but because they allow the dual use of the land to keep the agricultural use of the land. And with that, maybe you have access to much better land, like in Czech Republic, Italy, or Germany, or maybe it's the only possibility that you have for using land in other countries. So that's my talk, and thank you very much.
Thank you, Christian. Great to have these insights into an increasingly interesting use case for PV. A couple of quick questions for you before we move on. I think the first one that several people in the audience have asked is how does the risk of wind increase when you're working with a vertical installation, and how do you manage that?
Yeah, the wind is a clear consideration, and the dimensioning of the mounting system needs to be done properly to avoid that. So there are two solutions. The first one is when you have a plant to put a wind protection unit, just a very simple plank of something that breaks the wind. That is typically can be done, and it reduces the load. And the other thing is that the solar modules are made to withstand the full load capacity of the panel without any problem. They are fixed on the right points. Normally what you do, and this is going a little bit into the mounting system, you don't have just a surface of solar panels like you may have in a normal south facing. You build it with a little bit of space in between the posts and the module to always break the wind in a way that will save you from problems. But the same as trackers, you need to build the first line differently than the second and third and so on. That is the main point. Maybe let me add that when you have one added risk, which is wind, you lose one risk, which is hail, because the modules are not horizontal in any way, and the hail speed on the glass is much, much, much reduced.
Mm-hmm. And well, you've shown kind of how a vertical system can sort of reduce the need for investing in a battery. Presumably further down the line, there would still be an advantage in combining energy storage with a system like that.
Maybe let me tell you in a different way. We don't know yet the full legal framework in each country where batteries are going to be regulated. And there are many, many discussions about what is co-located conditions when you put the battery next to your PV plant, or maybe freestanding somewhere else that can be charged by the grid. And all of these have different technical conditions and different commercial conditions. And when there is uncertainty, maybe the right move is to prepare but don't do it yet until you know exactly how your business case with battery, how much arbitrage are you allowed to do, or you're only allowed to do load shifting, and so on and so on. So we think it's a low risk entry into the next generation.
Mm-hmm. Well, there is plenty more to discuss there. We will have to leave this topic here, though, and move on with our session. So thank you very much, Christian, for joining us today.
Thank you for having me.
And well, yeah, as we hear from Christian, heterojunction certainly has its advantages in vertical PV. And it is one of several cell technologies vying for space in a mainstream PV market that is currently dominated by tunnel oxide passivated contact, or TOPCon technology. But that is changing fast as manufacturers continue to innovate and compete to offer the strongest performing products. And here to tell us a little bit more about this market and how it's developing is a veteran of quite a few PV Magazine events, one who is always welcome back, Molly Morgan, Senior Research Analyst at Crew Group. Molly, welcome, and thanks for joining, and over to you.
Thank you, Mark. Firstly, it's a real pleasure to be here today. I'll quickly reintroduce myself. So my name is Molly Morgan, and I'm a Senior PV Analyst at analysis and consulting firm CRU. In my presentation today, I'm going to set the scene of the current status of PV market dynamics and also the cell and module technologies of today and of the future. So to kick things off, here are my key messages that I'll be discussing today. We'll start with a brief overview of supply-demand imbalance itself and how this led to manufacturers facing bankruptcies, and then we'll touch on whether this had any impact on technology innovations. Secondly, I'll move on to the technology status of the industry now, both in terms of the different technology capacities and the efficiencies of the mainstream technologies. And then finally, I'll round off the presentation by discussing the technology outlook for the industry for the remainder of this decade and beyond. So to begin with, very briefly, supply and demand. The graph I'm showing here shows Crew's overproduction estimates and forecasts throughout the PV supply chain, so from polysilicon to module, and these are normalized to end demand or our global installations forecast. For the PV industry, we believe that these levels of overproduction in the region of 20 to 25% would be deemed sustainable based on the annual growth rate of the PV market. And if you look to the graph and if you look to the levels of overproduction that were reached in 2022, you can see we reached levels far higher than what we deemed sustainable, with an average in 2022 of around 140%. Now, it's important to note that this overproduction, this didn't come from a lack of end demand, and we saw strong installations globally in 2023 and 2024, which is when that imbalance became significant to the market. And the effect of this overproduction was that inventory built up. And we believe that from our calculations, this built up to somewhere around the 250 gigawatt mark of excess stock in 2024, which naturally this led to extreme downwards pressures on prices. So as a result, manufacturers were left facing extreme competition and had to find a way to navigate negative margins or risk being forced out of the market altogether. Now, slightly more optimistically, looking to 2025, we have seen manufacturers be more conservative, both with their production targets and capacity expansion announcements. But as this overproduction has only recently realigned with installations, the result of this is that inventory, we don't believe that inventory has been able to be worked through at a meaningful level yet, or at least enough to relieve the downwards pressure on prices throughout the supply chain. But despite rock bottom pricing and manufacturers facing incredibly fierce competition, this definitely doesn't mean that innovation halted in the past few years. And throughout this time, we've seen an industry-wide transition from monoPERC to TOPCon and impressive efficiency gains for the key technologies of today, which are TOPCon, heterojunction, and back contact. So kicking off this slide, on the left-hand side here, we have a graph showing a current snapshot of the efficiencies of module product offerings in the market today. And this is an extract from one of our quarterly reports here. And each data point represents the average efficiency of a manufacturer's data sheet. And then also on the graph, the maximum efficiency of each technology category is represented with the X at the top of each column of data there. And then finally, the yellow diamonds on each column of data represent the average efficiency weighted by production volumes. So this is a really useful view, as with this efficiency distribution here, you can look at this and easily benchmark products and the different technologies and see how an individual PV module would compare to other modules on the market today. So immediately of note and interest with this data is you can see just how large the spreads of efficiencies are within each technology category. And so what does that mean? When you think about it, this can mean that the top performing mono PERC modules, even though today this is considered in most parts of the world a legacy technology, these best performing mono PERC modules will still outperform the bottom end of some of the advanced technologies, which really highlights the intricacies of procurement decisions. Secondly, you can see that TOPCon and heterojunction technologies are broadly similar in terms of average efficiency, but TOPCon, driven by recent impressive datasheet releases from Jinko Solar with its Tiger Neo 3 modules, has recently gained a meaningful lead over heterojunction in terms of the maximum efficiency. So this highlights the importance of analysing multiple aspects of an industry, as despite TOPCon and heterojunction having similar theoretical efficiencies, it's the low manufacturing cost of TOPCon which has allowed the technology to dominate in terms of market share today. So we believe that heterojunction might struggle to gain meaningful market share away from TOPCon with its higher manufacturing cost, unless the technology can establish a meaningful efficiency lead over TOPCon. But the efficiency lead that we believe would be necessary for that is one that we don't believe to be likely to be established as the technology category as a whole on average. So the last aspect I'd like to highlight from this left-hand side graph here is that the back contact technology currently leads the data set and the market in terms of maximum efficiency. And this has been the case for the last 2 years, driven by impressive efficiencies from manufacturers like ICO and Longi, who are really driving the technology category. But similarly to heterojunction, the manufacturing cost of back contact is currently higher than that of TOPCon. And so the manufacturing capacity for back contact remains small currently. And that's exactly what you can see if you look to the right-hand side of this slide here, where I'm showing Cruise cell capacity forecasts for 2025. You can see that TOPCon dominates in terms of manufacturing capacity over both heterojunction and back contact. And again, this is despite having comparable or higher efficiencies for heterojunction and back contact. But TOPCon isn't going to dominate capacity and production forever. So what technology transitions can we expect to see from the industry in future? My final slide here shows how we forecast market share as a percentage of production to evolve and change for the various PV technologies. Now, large-scale technology transitions can occur very rapidly when rival technologies can offer improved performance at cost parity to the current mainstream technology. And if you look back to 2023 on the graph here, you can see just how quickly the transition from mono PERC to TOPCon occurred. Now, looking to the future, what technology can rival TOPCon's dominance? From our internal efficiency forecasts at Crew, combined with our cost modelling forecasts, we believe that the back contact technology would need to sustain an efficiency lead of around 1.2 or 1.3% on average over TOPCon in order to achieve cost per watt parity. Now, with impressive efficiency releases from manufacturers, like I mentioned, like ICO and Longi in 2024 and 2025, we do believe that back contact will draw level and reach cost parity with TOPCon before the end of the decade. And that's why we believe that we might see a coexistence of the two technologies in the 2028 to 2030 timeframe. Now, if you've seen this graph before, you might notice it looks a little different this time around. And we now forecast a more gradual increase to the market share of back contact than we have with previous technology transitions in the past. And this is due to a few factors, and I can't get into them all today. But one of those is the fact that we forecast back contact to draw close to cost parity with TOPCon rather than a clear crossover, which has been seen in the past, for example, with TOPCon and monoperc. In the longer term, so 2030 and beyond, this is where we see tandem technologies really gaining momentum on a large scale. And this is driven by the market's strives for higher efficiencies that can only be unlocked by tandem devices. So to recap that overview for today, we talked how overproduction and supply and demand imbalance resulted in challenging conditions for manufacturers, but this didn't halt technology innovations. Then we discussed how technology categories compare in terms of efficiencies, but we can't regard efficiency in isolation, as it's the cost metrics that must be taken into account to forecast the future of the market in terms of technology transitions. And then finally, we looked at what we can expect to see from the industry from the rest of this decade until tandem modules begin to dominate in the 2030s. On that note, I'll hand back over to Mark and let him take it from there.
Thank you very much, Molly. I'm great to have your insights as always. And please stay with us as we head into this session's panel discussion. Well, as Molly shared with us, there are a few technologies vying for space in the market right now and more expected to make their way into this picture over the next 5 years. And we have assembled a panel of experts in the design and manufacture of some of these different technology pathways for what I'm sure will be an informative discussion. So now please welcome our other panelists on stage. We have Radovan Kopacek, Director at ISC Constance, and Ed Crossland, Chief Technology Officer at Oxford PV. And unfortunately, as I mentioned earlier, Fan Bin from GCL Perovskites was not able to join us at the last minute. But thank you to the other panelists who are here. I'll try and direct a few questions at each of you individually, first of all, but feel free to jump in wherever you have something to say. So Radovan, first of all, you've been a big supporter of back contact technology for a while now. Why do you see this as the best option for mainstream PV manufacturing?
Yes, hello everyone, and also congratulations to the presenters. Very, very nice presentations and very good analysis. Yes, so ISC Constance, we are there already since 20 years working on N-type technologies and since 15 years on IBC. So far, I would say we had a quite good crystal ball to look into new technologies, predicting bifacial PV coming, N-type coming. And I think it's quite straightforward development out there. You just have to look what everybody has on their technology roadmap, and also look into the past, what happened in the past. So there was a very fast transition, even if I believe it's really going too fast. But the Chinese are just really pressing, pushing, going towards higher efficiencies. So what happened in the past? There was a very quick transition from PERC to TOPCon, and similar things will happen now, going from TOPCon to back contact. And the reason is because all the production lines, like the classical production lines, are based on the same machines. It's only, let's say, the machines, the production line is a little bit more complex at the end, coming from PERC to TOPCon and going from TOPCon to back contact. But basically, it's based on the same technology, and with adding some machines going from TOPCon to back contact, you can have higher efficiencies. And of course, let's say the cost of ownership at the end will not be lower as for TOPCon technologies, but it pays off in the system. So the LCOE at the end will be lower.
And well, you mentioned there the risk of this, that you see maybe this transition happening too fast. I mean,
Yes.
what's the risk that you see there? Is it quality or something else?
Yes, it is definitely quality. So at the moment, there are a couple of players out there, as Molly said. It is Longi and Aiko. They know what they are doing. The quality at the moment is extremely good, and this is what TÜV Rheinland is always saying, that IBC is performing better than TOPCon. You cannot generalize, because TOPCon can only also perform very good. The problem is that what happened in the last 3 years, that there were newcomers even on the market, expanding the capacity and getting turnkey lines from Chinese turnkey providers. And because of that, the quality of TOPCon at the beginning was suffering. Now it's getting better, because let's say there is a washout of the smaller companies and only the tier 1 manufacturers are out there. But it will happen, I'm quite sure, in the future as well, when the producers will go very quickly now to back contact in order to reach the highest efficiencies. And this is also what China is asking for. Then also back contact will, let's say, suffer in quality also, because there will be more players out there, and the cost battle is of course out there. And in order to getting the lowest cost out, they will also cannibalize also, let's say, the performance, or let's say the BOM selection, the bill of materials.
Mm-hmm. And well, we see, these two manufacturers particularly that you've mentioned are really driving back contact for states to scale. Plenty of other of the big tier 1 players in PV are saying that they're sticking to TOPCon. Molly, I mean, you talked about kind of efficiency and cost parity, but are there other factors kind of keeping them from back contact or switching to any other technology?
Yeah, I think it's very important to remember how challenging the market's been for manufacturers over the past couple of years, which has reduced their cash reserves and meant that there's been less cash floating around for things like R&D and investing in upgrading lines and developing particular manufacturers' involvement in new technologies. And with back contact still being more expensive to manufacture right now than TOPCon, when you combine the fact that TOPCon does provide good efficiency metrics, it's natural that some manufacturers would be waiting and holding back to make that jump to a larger scale transition to back contact. But having said that, if you've been at conferences and trade shows lately, you'll notice that when you walk around, there is lots of manufacturers saying that they've got back contact pilot lines and they've got demonstration back contact modules at their booths. So a lot of the manufacturers, although they're not producing their own back contact cells and modules commercially yet, they have begun to lay the groundwork and to be ready to pounce and initiate a transition away from standard TOPCon to a back contact TOPCon design when the market conditions are less challenging, which is what we see to happen in that sort of 2028 earliest timeframe. But yeah, I'd say low profits have held manufacturers back, but that hasn't stopped them from preparing for that transition.
Mm-hmm. And well, then we come to the other technology that's increasingly moving into the mix. Of course, there's plenty of buzz around perovskites and tandem cells, and has been for a while now. Ed, welcome. What is your focus right now in terms of bringing this technology to scale?
Thanks, Mark. Thanks, everyone, for the interesting talks and for the invitation to talk to you today. I think I'd start by agreeing with the characterization of perovskite silicon tandems or multi-junction PV generally as a bigger jump in technology compared to what we've been discussing now, and therefore with associated bigger risk, but with certainly the same motivation that unlocking a higher efficiency potential across the board. And I think you can see that in how far tandems come since the first demonstration of the perovskite, which has really unlocked, I think, the possibility of multi-junction at scale, 10 years ago, starting around 10% efficiency, and now you can see the absolute efficiency in tandems has smashed it into the 35% for small area, 33% of big area, 30% at the module level, even now being reported. And I don't think it's shocking to say that the absolutely key part of the roadmap for really perovskite silicon tandem to deliver on that promise of a product realization at high efficiency is to be able to show durability of that technology in the high temperatures, high illuminations, high voltage stress conditions that the product will experience in the field. So just circling back to where are we right now? So we still produce in our German manufacturing facility in the low scale, very low scale overall, 10 to 100 megawatt full capacity in our first site. It was a first of a kind perovskite silicon integrated tandem cell production facility. And we've used that in the last few years to make and ship the very first tandem full-size modules, get them into the field, start gathering data, show those product proof points in terms of performance, combining in a product form the high efficiency and high reliability. And that, I think, the milestones on there, we have a very clear roadmap for what we expect to achieve in terms of that combined performance. That by a good milestone on that roadmap is to talk about the 2027 performance, where we see 1-2% and lower than 1% degradations in the field for a module technology that's 27%. And then year on year above that, we can go much higher. But it's that reliability that has held us to the product proof point status that we're at so far. That reliability topic is something that the Oxford BV technology pipeline, plus our partners, plus the wider research field, has been working on now intensively for the last 5 years, really focusing on the combination of those two things. And at scale, that means developing first the right cell build that does resist those fundamental degradation modes in the field. It means manufacturing with sufficient precision and control to first find, discover, but then avoid those critical defects that do lead to infant mortality of that technology, particularly in the perovskite submodule in the field. And it means doing it at both the cell and the module level. So sufficient encapsulation, I think that problem has largely been met already. And the fact that in the product level, you're limited by your worst cell and worst module, not your best. So that, I think, is where we are in terms of scaling the perovskite silicon. So two things probably now are focus. We've got the Brandenburg facility to the point where, with an extremely well-defined production process flow and set of processes, we've specified a process flow for much higher productivity manufacturing. That means at the gigawatt level for cell manufacturing, larger productivity platforms, which is required to meet the same price points for terrestrial deployment, even at higher efficiencies. But our intention remains, with sufficient investment or joint venture, to use that knowledge to expand our current low volume perovskite silicon tandem to the gigawatt level. And the second focus remains our product roadmap, right? Our facility has done those two things of demonstrating first product prototype and scaling, but we will go much further with that. And we see that the ceiling for the tandem perovskite silicon technology to be 35% plus at the module level. And again, as I've said, I think the efficiency is way ahead in demonstrating that at the cell level. The reliability is what needs to be leveled at those higher efficiency levels. And we continue to do that year on year with our production releases. So our current product is a 25% module level product, and now demonstrating 2% field level degradation. So good, but not good enough for mass deployment. 2027, we'll see 27% at the module level with 1% or below degradation levels in the field. And I think that's the really exciting level where we see full obvious choice for perovskite silicon tandem in many more deployment scenarios than are currently the case.
Mm-hmm. And I think when we look kind of at the wider perovskite community or sector this year, there's been some pretty interesting discussions about changes that are needed to the whole setup, to how they are tested, how they are qualified. Is that something that's going to take time as well?
I think that has come on a long way in terms of multi-junction efficiency certification. I mean, if you look back 10 years ago, that was a challenge even at the small cell level. That challenge has certainly been addressed by the third-party certification labs as well as equipment providers to be able to test accurately cells and modules at the full size. See, the bifacial tandem module ability to test is one that is probably the last milestone to fall in for the testing large areas. And I'd also think in the world of the R&D and development, all of the focus now is being transitioned away from those peak efficiencies to demonstrating peak reliabilities. And I think the community has also centralized or agreed around a much better protocol for perovskite specific and perovskite tandem specific stress conditions and testing, such that the now weight of worldwide R&D expertise focused on perovskite silicon tandem is now addressing exactly the right problem, being the field durability.
Mm-hmm. And well, if we come back to silicon PV side of things for a second, at Oxford PV, I think you've always worked with HJT, with heterojunction cells. Have you investigated some of these others as well?
Yeah, absolutely. So cell compatibility was a challenge we had right from the start, and as you say, we picked HJT early for lots of reasons. That it was the target for us as perovskite PV was very early on to make a high performance product type rather than a lower cost, larger area thin film versus wafer. So the whole argument now, I think, of combining this as a thin film technology on top of a wafer technology with the argument of addressing high efficiency is, okay, we were good to make that as an early call. I think that's still absolutely the right direction. HJT turns out to be also the easiest integration cell technology because of the, if you're talking about a cell integration level tandem technology, and of course, it's unfortunate the GCL guys aren't here because many others have approached this in a parallel way. We just call it module level integration of the two cell technology or two PV technologies where you integrate at the module level. And of course there, I think the compatibility with different bottom cell types is indeed easier in a module level integration. I think when you do that, you do have different manufacturing challenges to solve. You can either do that with the 4-terminal approach, which of course brings extra complexity and potentially cost at the system level, or there are schemes to voltage match the two modules such that you can do it with a 2-terminal configuration. I think that's super interesting. I think the challenges though of voltage matching in the product level, impact on the cell, silicon cell size and voltage level, stringing pattern for the bottom cell will be interesting to see how that comes out in the product. When you have the thin film technology on top of the wafer technology and you integrate at the cell level like Oxford PV do, then you get the additional benefit of reverse bias protection for the thin film cell from the silicon cell. So you have the shading resistance, and that eliminates another one of the potential field stability problems. You also have the challenge of, additional difficulty for the module optics, where you have two modules sandwiched together, where actually I think peak efficiencies of what's generally called 4-terminals or 2-terminal tandem technologies, yes, with the 4-terminal approach where you don't have to necessarily current match, the peak theoretical efficiency might go up. But I think the argument should still be more driven by where's the practical limit for the two technologies, and then when you consider it in that form, you have to look very carefully at things like optical efficiencies of the two sub modules or sub cells in realizing at the product level the full efficiency potential of the technology. So super interesting. I think both routes have got their slightly different challenges, but are really both totally viable concepts for a production tandem module that delivers, of course, lower LCOE, but based on a higher efficiency with sufficient reliability in the future. Oxford PV continue, and our own manufacturing is being based on, yes, the heterojunction as a bottom cell because of the ease of integration. I would say compared to other bottom cell types, that ease of there are certainly now integration routes fully demonstrated for the TOPCon and TOPCon types, and you'll see that the record cell efficiencies are pretty much parity for the highest efficiency tandem cell integrated on TOPCon compared to the highest integrated on a heterojunction. I would say the changes required to the TOPCon cell structure for a cell level integration are more than a heterojunction, and they're probably exactly the same when you talk about the module level or 4-terminal version of the product. But when you're talking about the cell integrated level, heterojunction is still where we're focused with our own manufacturing efforts. But like we say, I think we view this, and our expertise, of course, is really based on the top cell development and the recombination technology, but we see it as agnostic to the bottom cell. Ultimately, it will just be a different set of processes required for the integration.
Well, Radovan, is that is that issue of tandem cell compatibility something that comes up a lot with your work in back contact?
Yes, of course. So people are asking what will happen if you, let's say, if most of the production switches to back contact, and then the 2-terminal technology is the winner. I mean, this is not a problem because we will not forget how to produce TOPCon at the end. So this we could go back, but the question is, I mean, we are talking on technologies with a different technology readiness level, and to my understanding, going towards tandem, this will need more time. I believe that in the forecast that Molly was showing, because we are talking about evolutions, and now tandem would be a revolution. For me, it's clear tandem technology will come, but if you look at Molly's graph and you understand how many, what will be the production at that time, we are talking about 2 terawatt or 3 terawatt production. And I don't think that tandem until that time will become so bankable that everybody will roll out the technology towards terawatt. Of course, there will be multiple gigawatt, that's for sure, also for applications where you need very high efficiencies. And but to my understanding, back contact will be, let's say, driving our energy or electricity transition. But that's not a problem, because there is also something in between, which is a 3-terminal tandem, and we are working on that also together with ICO, and this could be also one of the solutions. And I think Oxford PV could also switch very quickly to that if, let's say, the integration of the cells will be solved. And we have some patent applications on that to interconnect also back contact devices with perovskite directly on the silicon. So I mean, the development will show, is it a 2-terminal, 3-terminal, 4-terminal, that it will come. It's clear, because then we can really go above efficiencies of 30%. But let me give you this message. In order to do the energy transition, it would not be necessary, because we are already the kings and emperors of energy markets. Even with PERC, we were already there. And in US, for example, all the producers at the moment are even starting with PERC production. I mean, it's a complete protected market, but still with PERC, you have also some business case if you produce this technology with a rather lower efficiency. And so we will see what the future will bring, but even back contact technologies have, let's say, good potential to become the bottom cells for tandem.
And is that compatibility something that the market is considering today? Could it be more of a challenge to scale perovskites with, if there is all back contact technology? Probably a question for Molly, first of all.
Yeah, so if the market does go in a different direction, kind of leaning on what Radovan was just saying, it doesn't stop our ability to have the solar market as a whole, and we'll still have installations, and we'll still have huge amounts of production that can support the energy transition globally. So I guess my personal view on that is that if there is a change in direction and we do have to scale up a different capacity to support a particular technology transition. If it were to delay a technology transition by a couple of years, it's almost not a worry for me, because we've still got great amounts of good capacity, and we can continue to produce good modules in such great scale that we're not even using the vast majority of the capacity that is already installed today. So although it would be a challenge, it might delay a scaling up of silicon perovskite tandems, it's not necessarily an issue, in my belief, if that were to be a temporary bottleneck.
Mm-hmm. Sure. And well, so Oxford PV this year announced a big partnership with a tier one manufacturer. Of course, Ed, you can only say so much publicly about that partnership. But how does working with a company used to that kind of scale, how does that influence the development of tandem technology?
Yeah, you're right. I can't reveal all that many details about the deal, but let me comment on a few things around that, what that announcement was and what it means. In April of this year, we announced that we've granted exclusive license rights to Oxford PV's fundamental patent portfolio for perovskite photovoltaics, so both single junction manifestation or multi-junction product types. And we're totally delighted that Trina Solar, which is one of the world's leading solar manufacturers, will be able to offer that perovskite technology via that access to the Chinese market, both directly and via sub-licensing to other people. We see it as a big milestone in what has been our mission for many years, to make perovskite as a material discovery relevant in mainstream PV. So we cannot, as Oxford PV, and should not try to do that alone. So we recognize that the knowledge, experience, manufacturing capability that Trina and many other people will have. So while the deal is actually access only to Oxford PV's patent portfolio, so both companies do retain their own, well, have and retain their own know-how in the field. Nevertheless, you can't introduce a new PV technology without elements of both the technology innovation, the scaling, and the manufacturing know-how comes together. So it totally strengthens the position of Oxford PV and other players, but also the prospects of bringing perovskite silicon tandem products available to the market as soon as possible.
Mm-hmm. And well, Radovan, at ISC Constance, of course, you're also no stranger to partnerships with those manufacturers operating at very large scale. Do you see already the people you're working with asking about tandem technology, and what do you tell them when they do?
Yes, so I think it's the best to look at the Indian market. We have helped in the last 1.5 years to set up TOPCon production for 4 companies, and they are already asking how they can, let's say, upgrade, or how they can go to the next level, going back contact. And there they are saying, of course, we will like to do that maybe in the coming 4 to 5 years. Of course, they are also asking about tandem. Is then back contact capable to go towards tandem? But mostly they are, let's say, aware that it will take longer time because of some challenging challenges in the tandem technology. So they are asking more or less, we have to do that also to attract investors, of course, how our crystalline silicon cell line can be upgraded to tandem. So we very seriously already talk about back contact, and then have to show a concept that it could be applicable also for tandem. But let's say it is more important for them to have already a plan how to go towards back contact first.
Mm-hmm, sure. And how important is this kind of model of sharing technology and partnering, across the industry? How important is that to the future of PV?
It's a question for me?
Sure, yeah.
Yes, I think it's very important. I mean, we have to do the technology transition or the electricity transition altogether, and we just cannot rely on one supplier which sends the modules to all around the world. And it's about resilience. I mean, in 2050, there are some serious forecasts where 80% of the energy will come from PV systems, because PV is getting so low cost with a combination of with storage even, that this will happen. This will be our major electricity source or energy source even. And just to leave it to China, it's very dangerous, and that's why we try since a long time to establish also now again PV production in Europe. This is difficult because you need also some protection, or at the beginning at least, or some money. And in the last 5 years, we burned some ground in Europe because of insolvencies, and it's continuing with Meyer Burger. So it will be really difficult to convince investors to go into this direction. But what we are doing, we are partnershiping at the moment with Indian companies. So we are still practicing, with ISC Konstanz, how to set up gigawatt production abroad. Also in US, we have a company that we are cooperating with on PERC production. And hopefully in let's say after 5 years, the situation in Europe will be a little bit better, so that we can set up also PV production in Europe, because really we are talking about the new oil.
Mm-hmm. Ed, Molly, anything to add on importance of partnerships across the industry?
I mean, I certainly agree with what Radovan has just characterized there. And from the Oxford PV perspective, we have partnerships that are based on IP only collaborations, in particularly in our technology, but we also have approaches and concepts for anything on the spectrum of partnerships, collaboration, joint venture, of bringing the perovskite silicon tandem in this case to manufacturing, echoing what I said before, that you need that with both the innovation of the technology level plus knowledge of scaling and combinations with the bottom cell technology and with the modularization and the classical aspects of scaling PV technology. So Oxford PV are ourselves open to both concepts for exactly that, the same reason Radovan said, that bringing that into to the world in the quickest possible way is benefit to us all.
Mm-hmm. Sure. Finally, Molly?
Nothing further to add, apart from to say that I completely agree that the collaboration and partnerships, if we're all working to that communal goal, it seems like an obvious way for someone like me who's slightly more removed from dealing with the intricacies of how those partnerships actually work. But it seems like a very sensible way to continue working together to that electrification goal.
Mm-hmm. And of course, talking about partnerships does kind of lead us to the slightly thorny issue of managing IP, intellectual property. I mean, I think, Radovan, you talked about manufacturers in the US sticking with PERC cells. Is that partly down to IP issues with TOPCon?
Absolutely, yes. But it's not the only thing, of course. I mean, we know that in US, First Solar is holding quite a strong patent, and a couple of companies are now starting to produce PERC, like Q-Cells, ES Foundry, Saniva. But I would say also one of the major issues is starting production in a country which is, let's say, which has forgotten about the ability to produce solar cells. Starting with PERC is also dangerous, because you have to have really a good knowledge, process know-how. And starting PERC is quite simple. You don't need very strict clean room conditions, and that's why Saniva, they wanted to go very quick. Also, the ramp-up time is much shorter to benefit from the IRA. Now it's this beautiful bill is still out there for a couple of years. So at the moment they are really doing good business. So PERC is a perfect solution for them. And regarding IP, there are daily news out there who agrees with let's say there are many agreements out there. For example, I just read yesterday that JS Solar are now they exchanged some patents on TOPCon with Chint, with Astro Energy, and now it's okay again. And but let's say going into TOPCon, it's really a minefield of patents. Going into back contact or heterojunction, it's not that difficult because Sanyo and SunPower, they already have been working on that since a long time, and many patents are already expired. However, there are still patents also in the back contact arena, and then of course Maxion is now talking to ICO again, and but ICO has secured, and so does ISC Constance as well, and Longi, their own patent portfolio. So it's not that difficult to let's say start production in the back contact arena, and that's also why a couple of people are already considering to start with IBC and not select TOPCon. However, I mean, at the end, you cannot guarantee completely the freedom to operate, because if a company wants to sue you, they just do.
Okay, sure. Well, we have a couple of minutes left, and I mean, we can't talk about PV technology and manufacturing in 2025 without mentioning the market situation and the oversupply that has really pushed prices impossibly low the last couple of years. How do you feel that current market situation is affecting innovation and the implementation of these new technologies that we've discussed over the last 30 minutes or so? Molly, probably first of all.
Thank you. So I did touch on this very briefly, but I'll recap, and then I'll allow Radovan and Ed a chance to agree or disagree. But I think what's clear to me is that although conditions for manufacturers have been incredibly challenging over the past few years, so especially in 2024, we've seen just how resilient manufacturers and the market as a whole can be. And we, for example of that, we forecast that a number of manufacturers would go out of business in 2024, and it's been really quite surprising and impressive, the amount of manufacturers that have been able to stay in business that we perhaps thought might struggle a bit more in 2024, which really highlights how resilient the market is as a whole. And then despite this, even though I mean, it's incredibly difficult to say how market shares would have changed if we didn't have this impact on prices falling below cash costs, etc. But it's also clear to see that there's been other forms of innovation that haven't been purely technology related in this time as well. So we've seen obviously larger wafers, rectangular wafers, innovations with bus bar formats. So there's definitely been innovation, and it's really great to see that the market's still moving forward and striving for increased performance, even though things have been particularly challenging.
And well, Ed, how do you see the current market situation for PV modules?
Let me try and cheat and answer this in two ways, because of course it would certainly, as a new technology or the prospect silicon technology, subject to the same pressures of cost in planning as other PV, squeezes the space for demonstrating improved LCOE via a higher efficiency technology. People will pay more, but only a certain amount more for improved module performance. So that certainly has put pressure on on our own roadmap, and most directly in our ability to close funding from capital markets for our own volume scaling plans at a time when the oversupplies are pressured. cost of the traditional PV. However, that's given us maybe a slight backhanded advantage that we've demonstrated key progress on the roadmap in the meantime, which is a key component of reaching those larger deployments in the future. And in the meantime, we don't only make terrestrial module and cell products, we also have taken the opportunity to make and sell high efficiency tandem cells during that roadmap development phase into what we call specialty applications, but where anywhere where higher efficiency has a higher value to the customer and therefore potentially lower volume, of course, but higher value in the meantime to make a case for the tandem. And remember that as a new technology, the quicker we can get out in the field in any product form and generate real data, the more the risk level and the appetite for people investing in the manufacturing becomes more comfortable with the idea of going quickly to scale. And as we've said throughout this whole panel, the cost points that you need really rely on that scale. So there's no way around that. There is a barrier to realizing those cost levels, which is your manufacturing capacity. It takes time to build that, and you have to be ready to accept some risk in doing so. So good, some good, well, mostly bad, but there we go. We've written it out quite well.
Okay, and Radovan, a few words on challenges in the current market environment.
Yes, I mean, we all know the challenges that let's say mostly in Europe, the module prices are extremely low. The Chinese government is also somehow trying to tell to the companies that in future they should do more profit, so they are regulating things. And what I heard now at the last workshop in Yiwu, which we organized together with ICO, there were some rumors that it's not allowed anymore to build a new production capacity in China, so we are not allowed to build new factories. And I think in order to really increase the volume, or let's say the power in the factories, is to be innovative and going from TOPCon to back contact. And it's quite simple to go this way. Definitely on module level, for example, if you have a module factory producing TOPCon, it's already capable to produce back contact, because this is what we invented in the past, how to use simple stringers to do to produce back contact. The stringer has to be only modified with a very low-cost procedure, and you can go easily to back contact. And I also think that now ICO will also change their strategy to be again a solar cell producer, like they used to be in the past. They produce, let's say, the PERC for all the or for many module producers in China. Maybe this will happen also in future. And so I believe that actually back contact technology will come quicker as we think.
Mm-hmm. Well, I think that is a strong point to close on, and we are just about out of time there. There is a wealth of innovation in the PV industry, still new targets to aim for long-term performance at scale, material consumption, and of course, cost. We shouldn't forget, though, that solar has come so far already, and we have the technology that we need to keep on deploying and pushing solar to the center of the world's energy mix. Thank you once more to Molly Morgan, Radovan Kopacek, and Ed Crossland for taking the time to participate in this panel. It has been a pleasure. Now, all of those
Thank
technologies...
you very much.
You're welcome. Thank you. Well, we move on now to the final part of this session. Now, all of those technologies that the PV industry has built up to massive scale, the new ones being implemented today, and those that came before as well, all of that is built on the hard work of universities, research institutes, and R&D departments the world over. And my next guest knows this all too well. Down in Australia, the University of New South Wales, UNSW, has played its part in developing many of the technologies we see on solar manufacturing lines today. And it continues to work on those we might see in the future as well. So I am very pleased to welcome Alison Ciesla, Professor at UNSW's School of Photovoltaic and Renewable Energy Engineering, for a quick chat about the school's priorities and what's causing excitement in PV research and development right now. Alison, welcome.
Oh, there we go. Hi, thanks. I wish I could say I was a professor. I'm not quite there yet, but I'm very happy to speak here on behalf of many of the amazing professors that I do get to work with. So I've had a little bit of a chat to lots of them in the lead up to this, just to make sure that I can try and represent everyone a little bit fairly and not just myself.
Well, wonderful. Well, Alison, as a researcher, then not quite a professor, do you see more improvements to silicon PV making their way into manufacturing in the coming years? Is there still more work to be done here?
Yeah, I think that's an interesting question, because it depends a little bit what you mean by improvements. So I guess there's a lot that can still be done. And I think the industry have just been moving so fast and adopting technology so quickly that it almost feels like anything is possible at the moment. And the performance of the silicon cell is, reaching the fundamental limit. But I think there still is more to go. So I think Professor Dan McDonald from ANU in Australia has given some nice presentations recently looking at, where are the bits of energy that we can get more out of the solar cell, and the TOPCon has kind of reached heterojunction now in voltages. So really, we're now looking at trying to get more from the light, so get more current out of the cells, which I guess is where we're going to eventually get to more out of the spectrum when we get to tandem. But I guess for silicon, we're seeing so much happening in terms of even like the wafers are near perfect now. Longi's done amazing things in improving wafers, and they're still innovating, introducing, antimony dopants and things. We're getting near perfect surfaces, but, exploring all new materials and different types of passivation. And this has now opened up, made rear junction now a very ideal option. So we don't have to have limiting front diffusion, but at the same time, patterning and alignment has got incredibly possible, and so you can do much more localized features with doping and things. And this is where we're now seeing back contact take off, where we've seen a lot of talk about that tonight. And I think that I think we'll probably see a lot more of that as it's becoming so feasible. I guess even with Longi, like there's so many options even within back contact, where you can have a whole family, you can have different passivation techniques even within the back contact. So I just feel like almost the possibilities are endless. And where I think it was Radovan mentioned that, we're operating, there's so much losses at the moment in the market that I think being able to move into a bit more niche product might enable a bit more, asking for more price. So I think it would be nice to see a lot of that. But I guess beyond that, if you're talking about improvements in terms of LCOE, as I think Radovan also mentioned, we're not just talking about, how efficient the cell is, but how it performs in the long term. There's a lot to do in quality and durability, and that's where my space lies. And I, collaborate quite closely with Professor Bram Hooks here, who does some really amazing research looking at, compatibility with materials, whether it's, soldering flux and encapsulants or metal pastes, and now UVID, which is becoming a huge issue as we're trying to get the UV light energy in the solar cell, and it's harming the front of the, the silicon and the passivation and everything. So I think there's still a lot of things that can be solved and improved there. And then, so I guess a lot of that, then if you're looking at optics and durability, a lot of that comes down to materials and module properties. And so I think we're going to see a lot more innovation in those spaces. So we're, I guess, more coatings on modules and things, whether it's thermal properties or reflection that I think, was it Christian, the first speaker, was talking about, or anti-soiling even, like anything that can try and improve your, LCOE or operating properties. And I think a lot more like coming back to niche products that might be able to command a higher price, module specific designs. There's a few manufacturers now offering these in some format, but there's so much we can do in that space. If it's things for like a vertical installation that Christian was talking about, or depending on how it's installed, where it's installed, or if you're, for hail resilience maybe, or thermal cooling or something. So, and I guess that one more factor that there still is, if we're talking about improvements, could be material usage and sustainability, which is a big focus of Associate Professor Brett Hallam's work here with me, and he's doing really amazing things, reducing silver and bismuth through like quite innovative metal printing designs that, you know, he's already reduced metal like silver printing by up to 40%, and he predicts that he could get it to 85% with dedicated pastes. So, you know, I think that, yeah, there's a lot happening. I think it's endless, and I could probably talk for an hour on this if you let me.
Sure. Plenty going on. And a lot more to come on module quality and durability in our session this afternoon. Please join my colleague then for that later today. But Alison, for now, as we heard in the panel just now, perovskites, tandem cells are seen by many as the next step in PV technology. Are you working with these materials at UNSW, and where do you see kind of the key remaining challenges?
Yeah, I mean, it's a good question. So there's a lot of perovskite work going on. So I think Professor Xiaojing Hao here at UNSW, so she's, I think, quite well known in perovskite space. She's got, you know, a new record this year for a small area perovskite, but yeah, her group work also on other materials as well. And, you know, they're doing some really amazing work on, you know, like improving that, but also other aspects. So I think Ziheng is from her group, and he's been developing conductive polymers that you can deposit onto glass to replace the TCO and encapsulant that have, you know, better properties and less absorption. So I think there's a lot of stuff happening in that space, and this is not totally my expertise, so I don't want to I don't want to step on anyone's toes, but there is a lot going on here, and I think it is exciting what's happening in perovskites. And I was very excited seeing all the manufacturers really start to embrace it in R&D and start trying large area cells and things. I think the enthusiasm's backed off a bit now, and potentially what looked like maybe going to be in the market in the next couple of years is now maybe looking more like 5 to 10. But yeah, what's been happening is really impressive, and I think all the developments will enable, you know, perovskites or whatever tandem top cell might happen in the future. It's, you know, it's a huge progress for the entire industry to be starting to make these types of cells and modules, even like 2-terminal, 4-terminal modules out there. I think it's a really cool time to be watching all this. But I think the stability at this stage, I think, is just far too limiting to say that it's close on the horizon. I think from my understanding, it's, you know, going to the higher band gap and the larger area depositions that make it a lot harder to make it stable. So I think trying to get those materials there will require a fair bit of work going forward.
Mm-hmm. And well, jumping now straight to another area entirely. I know UNSW has been among a few universities that's announced some impressive achievements with Kesterites, with those copper, zinc, tin, sulfur cells recently. How do you see the potential for this material?
Yeah, I think it sounds really interesting. So Kaiwan he's a researcher here that works on that. And you know, Kaiwan's lovely. He's too humble about his research, but when I speak to others, they tell me how incredible the work is that he does. So he's had some records this year, I think, on small area cells as well. And from what I understand, the potential is great because it's, you know, a very abundant material. It's incredibly stable, so they don't have all those same challenges with perovskites that they don't even really need to test the stability. And they can use, you know, cheaper abundant metals like aluminium. I think Kaiwan sold it to me as a, you know, one of the challenges is that it needs high temperatures and things. But in my understanding, you know, one of the benefits of the TOPCon technology is that it's made with high temperature, which enables a greater stability than heterojunction. You know, like if it's made at lower energy, it probably has less stability under energetic conditions in the field. So I think that might actually be a selling point. But yeah, so I think defects and efficiency are their biggest thing as they try to scale up the Kesterites. But it sounds promising, and I'm really keen to see what they do next.
Mm-hmm. And I know recently you had some interesting findings with singlet fission as well, and that's technologically that sounds like a pretty amazing thing. Could you tell us a little bit about this technology and whether there's commercial potential there already?
Yes, Great question. So this is a project that I found myself roped into. I was brought into the project as the durability, reliability person, and I knew nothing about singlet fission. And now, a few years in, I think that it's a very interesting technology. So I guess for people who might not be aware, like I wasn't, it's kind of like a tandem cell. So it puts, the idea is we put a layer on top of an organic film on top of the solar cell that can absorb the higher energy light. So I guess that first of all protects the silicon cell from UV, but then it also creates 2 electron hole pairs from each one. So it goes through the fission process. And then what we're working on is trying to now capture those extra electron hole pairs into the silicon. And because they're just both injected across one circuit, it's not actually a second junction cell. There's no complex interconnection. There's no current matching required. So it's a really simple and nice technology and has a very similar efficiency potential to a 2-junction tandem. So I think it's such a cool prospect, and it's had very, very little R&D put towards it compared to things like perovskites. So I'm so excited to see where this technology can go once it has, much more momentum of R&D behind it. So when you talk about it saying commercial potential, I think we are actually trying to commercialize now, which might seem crazy because it is still quite a low TRL technology. But if anyone knows the Universal Display Corporation model, where we really want to try and leverage that type of model, where if we can commercialize now and build a platform and focus on industry type R&D rather than academic, where everyone works in silos and we have to wait for it to take on and everyone to get a grant and slowly build. We want to do it through like a large scale industry open innovation type of development and see where we can take this, because we're working with leading researchers in chemistry, Professor Timothy Schmidt, who has done a lot of the groundbreaking work in this type of molecular chemistry, and MIT researchers under Professor Mark Baldo, who have had some really, really great results in this. So yeah, this is something that I'm really excited to see where we can go, because it's a nice alternative to perovskites, but with similar potential.
Okay, well, yeah, that's fascinating to hear. We are just about out of time, but I'll squeeze in one last question for you, Alison. Beyond these, is there anything else really that has you excited in solar R&D at the moment?
Yeah, there's a lot. I could talk for hours. So I guess just to maybe list a couple of things. So I guess between now and maybe singlet fission solar cells or tandems, I think there is a lot we can do in the encapsulants or even films with similar types of multiplication techniques, but in rather optical ones, where we put things in the encapsulant. So there's already downshifting, kind of one photon in, one photon out to minimize UV. But what we're looking at doing is similar to like a singlet fission, but rather an optical process where one photon goes in and then 2 come out to get extra light out. And it's not quite got the same efficiency potential, but it can protect from UV and get an extra boost out of the silicon cell. And similarly, up conversion to try and get more out of the light, the IR light in the spectrum that's also currently wasted. Then I guess there's going to be a lot of new stuff happening with new materials. We've got a researcher here, Tong, who does generative AI stuff, and they're looking at doing self-driving labs with Monash University to develop new materials that, they might find a stable perovskite, or they might find a new singlet fission material, or I don't know, like they can explore spaces widely beyond what we could with just normal manpower. So I think that'll be super interesting. And we just got a new head of school here, Professor Eakenstalks. If people haven't met him, they should. He's amazing and such an optimist, and he wants to do all these cool things like adding electronics to the back of the cell, or he's just looking at doing PV at night at the moment using thermoradiative diodes. So yeah, there's a lot. Oh, and sun drive. So I'm probably biased here because, my dad did a lot of copper plating on his original buried contact solar cell and then the Pluto cell with Suntech. But SunDrive have, invented an amazing copper technology that's broken efficiency records and achieved high yield. And now they're working with Maxwell and Vista, I think, to build an actual commercial plating tool. So I think that's something that might be interesting in future as well. And I guess if I could just say one thing, because I think there's so much exciting stuff happening at UNSW and across all of Australia in general, actually. And we have an Australian Centre for Advanced Photovoltaics that kind of links a lot of the great research facilities and researchers in Australia with networks across Australia. And I've been at a conference this week with them, just looking at some of the great work. But they have a program now that was set up by my colleague Jessica, and it's like an industry partnership program where industry partners can come and sign up to work with our network. So I just wanted to mention that in case anyone wants to collaborate, because there's a lot of good stuff going on.
Okay, sure. Well, yeah, it's all fascinating stuff. And as you say, we could talk about this for hours. Unfortunately, though, we are just about out of time for this session. I think that is a strong point to finish on, though. So thank you once again, Alison Ciesla at UNSW, and thank you for joining us. I know it's getting late over there as well, but it's been a pleasure speaking with you, and goodbye for now.
Thanks, Mark. See you.
Well, thanks once more to Christian Comis for his presentation earlier in this session, and to Molly, Radovan, and Ed for an enlightening panel discussion. And thanks to all of you for joining us as well today. That is just about all we have time for in this session. Visit pv-magazine.com for up-to-the-minute news on solar and energy storage. And our final magazine edition for 2025 is out this Friday, packed with the latest on grids and negative prices, as well as manufacturing and technology news, of course, as well. And PV Magazine Week Europe continues this afternoon. Do join us again at 3 p.m. Central European Time, when Marianne Valloon will be in the studio with yet another crop of carefully selected PV technology experts to discuss ultraviolet-induced degradation, among other threats to module quality and performance, and how the industry is dealing with those. That's coming up today at 3 p.m. Join us then. Goodbye for now.